All right, this is a look at two example questions that deal with thermodynamic processes. The first question is a process that starts with an adiabatic compression. Now, this question is not going to contain any numerical values, so it's just going to give values in terms of P and V. So in this question, it begins at point A, which has a pressure P and a volume of 6V, and the question's asking to first draw this process. So the first step in this process is an adiabatic compression. It compresses to a volume of 2V and 6 times its original pressure to 6P. The next step is an isothermal expansion to state C. Now we don't know where state C is from the problem, but it does say that the process is isothermal. So from the ideal gas law, temperature is PV over NR. Because the amount of gas here is fixed in a closed system, N is going to be constant and R is a constant, so temperature will be directly proportional to PV. At point B, the value of PV, which is 6P times 2V, is 12 PV. So I want to find a point where the volume is 6V and the value of PV is 12 PV. And that's going to be at a pressure of 2P. So point C is here. And that's what the isothermal process looks like. Now, for any isothermal process, it's going to be less steep than an adiabatic process, which the graph shows here. Finally, the gas is going to return to its original state at point C, so it's going to decrease pressure at a fixed volume back to point A. Part B asks to explain why the internal energy of the gas increases from A to B. Qualitatively, what's happening here is that the molecules are hitting the piston, which is moving towards them because the gas is being compressed, and after they hit the piston, they speed up. This is an elastic collision, so when the molecules move away from the piston, they're going to have to be going faster than when they approach the piston, since the piston doesn't change directions. In this case, it's adiabatic, so Q is 0. So if no heat is added or removed, delta U is going to have to increase in this case because temperature increases. Part C asks if heat is added or removed, going from state B to state C. So this is an isothermal process. In an isothermal process, there's no change in temperature, so there's no change in internal energy, and delta U is 0. Now quantitatively, looking at the first law, delta U is 0. And then looking at the graph, I can see that the gas is expanding, so there's negative work being done. So if there's negative work, that means that Q has to be positive. Now conceptually what's going on is that the gas molecules are the same temperature, so they remain at the same average speed. However, there's negative work being done on the gas, which means that the gas is expanding, and normally when a gas expands, if there's no heat exchange, the molecules are going to slow down. In order to stop the molecules from slowing down, heat needs to be introduced into the system to give them enough energy to not slow down when negative work is done. Part D asks to determine an expression for the heat added or removed from the gas, and that's going to be an expression in terms of P and V. And this is going from C to A. So going to the first law, delta U equals Q plus W. What makes this part a bit easier is that going from C to A, there's no change in volume, which means there's no work done on or by the gas. So delta U here will be equal to Q. To find delta U, because U is equal to 3/2 PV, I can do 3/2 final pressure times volume, which is at point A, minus the initial pressure times volume at point C. And this gives that delta U is equal to -9 PV. So here, heat is removed through something like an ice bath, and what that's going to do is, as the volume is locked in place, it's going to decrease pressure, which pressure is looking at how fast the molecules hit the container by slowing them down. The last part of the question here asks if heat is added or removed in one complete cycle. So any complete cycle is going to start and end at the same point. So it's going to start and end at the same temperature. So delta U is always 0 for any full cycle. And from the first law, If delta U is 0, then Q will just have the opposite sign of work, which I can also get the sign of work from the graph. So here I have an compression going from A to B. The compression is going to have positive work, and then I have an expansion going from B to C, which has negative work. C to A, of course, has no change in volume, so the work is 0. Now, there is negative work and positive work on this graph, but the negative work is higher on the graph, which means it has a greater magnitude, which makes the net work negative. And since the net work is negative, that means that there's heat added to the gas since Q is positive. The second question deals with another thermodynamic process. In this case, there's numerical values given for the PV diagram for a process where a gas goes from state A to state B to state C, back to state A. The first question asks to calculate the temperature at state A, shown on the graph. From the ideal gas law, pressure times volume equals number of moles times the gas constant times temperature. So solving this for temperature, I get PV over NR. In this case, the number of moles, N, is given. And the temperature at A is about 577 Kelvin. The next part looks at the part of the cycle going from state A to state B, and it asks if in this process heat is added or removed. So the first law of thermodynamics says that delta U, the change in internal energy, equals Q, the heat added or removed during the process, plus W, which is the work done on or by the gas during the process. Now, since the amount of gas is fixed and internal energy is based on the amount of gas and the temperature, U here will be directly proportional to temperature, which is directly proportional to PV. So going from state A to state B, the pressure remains the same, but as I go from A to B, the volume goes down. So since pressure times volume, that product is going down, that means the temperature goes down from A to B, which means the internal energy decreases. So in this case, delta U is negative. I can also see from the graph, since the volume is going down, that the gas is being compressed. Since the gas is being compressed, that means the work is positive. I know that whatever Q is, plus a positive number, has to equal a negative number. So in this case, I know that Q is negative, which means that heat is removed. Qualitatively, what's going on here is that the molecules hitting the piston should speed up the molecules and result in an increase in temperature. Since this is an isobaric process, the molecules can't speed up, and in fact, they need to slow down to keep the rate of collision that the molecules make with the container constant. This requires removing a large amount of heat so that the slower molecules hit the container at the same rate that the faster molecules were hitting the larger container with. The next part looks at the heat added or removed going from A all the way to C. And here again, I'm going to use the first law of thermodynamics, where delta U equals Q plus W. And I can find delta U and W from the graph. First, I'll find delta U. So U was equal to 3/2 nRT. And then combining that with the ideal gas law that PV equals nRT, I can say that U is 3/2 times PV. So to find the change in U going from A to C, I would do 3/2 pressure at C, volume at C, minus the pressure at A times the volume at A. And for this process, I get that the change in internal energy is negative 6,600 joules of energy that's lost. When it comes to finding the work from A to C, I only have to look at the part of the graph from A to B, and that's because going from B to C, there's no change in volume. So the work here is 0. To find the work from A to B, I'm going to find the area under the graph. Now the area under the graph means I look at the process and then find the area of everything underneath it, which would be this shaded region here. Now, this shaded region is a rectangle, so to find the area, there's a height of 8 times 10 to the 5th, and a width of 4 times 10 to the negative 3rd. If I multiply those two together, I find that the work is positive 3,200 joules. So coming back to the first law, I have delta U, which is negative 6,600, equals Q, plus 3,200 joules. That means in this process, Q is going to be negative 9,800 joules, which is heat removed. The last part asks to calculate the heat added or removed for the entire cycle. Again, I'm going to go to the first law of thermodynamics. Delta U equals Q plus W. Now, for the internal energy, it's based on the value of T times V. For one cycle, I'm going from point A back to point A, so obviously PV is not going to change. So for any full cycle, delta U is 0. So the heat's just going to be equal to negative work. Now to find the work, I'm going to do the area of the graph. This is a bit different from the part above. I was just going from A to B. That was the area under the graph. For the full cycle, I'm going to take the area of the graph, which would be this triangle here. So the work is going to be the area of that triangle, so it'd be 1/2 base times height. The base would be 4 times 10 to the negative 3rd, and the height would be 6 times 10 to the 5th. So plugging in numbers there for work, I would get that the work is 1,200 joules. Now that area is not going to give me the sign of the work. To find the sign of the work, I just look at the graph. There's a part with negative work down here, but the part on top, which is the compression from A to B, that has positive work, and that positive work is going to be of greater magnitude, which makes the net work positive. So if the net work is positive 1,200 joules, then the value of Q, the heat removed, will be negative 1,200 joules.